let's do energy rate balance to analyze its temperature distribution under different surface conditions. We have a tube here with a uniform mass flow rate at the inlet, here, and the fluid is at the mean temperature, say, at the inlet. And if we would like to know how the temperature distributes for everywhere inside the tube, we know we are going to do energy rate balance. But the step before that is define our control volume. What kind of control volume should we define inside the tube? We need to define a differential control volume, like the way we derive our heat diffusion equation. We pick an element fluid here, and let's say it is, we designate the inlet as our origin, and it has a length between the inlet as x, and the element itself has a dimension of dx. Then we pick a differential, a control volume of the entire cross-sectional area, but at the length of dx. Then we can establish our energy rate balance, QE minus Q out plus Q generation equals heat stored inside the control volume. For this case, let's just assume for a heating case, the surface of the tube is at a higher temperature than that of the mean of the entire fluid inside. The next step for us is to identify all those four terms inside our energy rate balance. To make our calculation simpler, we can make several assumptions here. If we, for typical cases such as heat exchanger, because the tube is long, and we can assume it is running at a steady state. What does steady state mean? Nothing changes with respect to time. And how does it reflect in our energy rate balance equation? Which term contains a time constant with relates to time? Heat stored, right? Because for the first class we learned heat stored is how the enthalpy varies with respect to time, right? But let's assume everything is in steady state. So this term goes there just by our assumption. The second assumption we are going to make is that let's neglect all the possible heat generation can be reactions, chemical reactions, or friction heat loss. Let's assume it is negligible. Then we would have our generation term equal 0. And with those two assumptions, we end up with QE minus Q out equals 0. Then we need to identify what is Q in, what are heat transfer mechanisms associated with our Q in and Q out. For a running tube, inside this differential control volume, where is Q in? Fluid move inside, right? By advection, we denote it as Q advection. Yeah. And of course, fluid moves outside the control volume. So takes heat out by advection. Heat out anything else. And I assume the temperature of the surface is higher than the fluid. So yes, it gains heat from the surface through convection. Anything else? Convection? Does it? May I ask you? Does it lose heat by convection? No, because the tube is at higher temperature. It gains heat through convection, not lose heat. How about conduction? Yes, because when the fluid comes at this part, this gets heated by the pipe, right? Then perhaps at the part here, the temperature should be higher than the inlet. That's how heat exchanger works. And why? Let's make our third assumption here. And because due to the temperature difference here and here, it must have conduction. But let's assume it is negligible compared to the vigorous advection. Conduction in this length, in the direction of the tube length, is negligible compared to advection. With all those three assumptions, we have our QE just by heat transferred in by advection in. And for a hotter tube, it gains heat through convection. And for Q out, just this term, the heat transfers out from the control volume by advection, Q advection out. And if we put those terms together into the energy rate balance, we have our Q advection in minus Q advection out plus Q convection equals 0. That's our energy rate balance, with all those three assumptions made. Let's deal with Q advection in minus Q advection out first. We have learned this on the first class of 6th week. Advection in. What's the expression for advection term flows in?
No, I don't remember.
But it's now for advection, mass flows in, right? So it must associate with some mass flow rate, right? And the energy times the enthalpy it brings in. I write like this: the mass flow rate times the mean. The M does not mean mass. Mean enthalpy, X, at the location of X, because in the defined control volume, it flows in at the location of X, flows out at the location of X plus dx. So similarly for the Q advection out, we minus mass flow rate times the mean enthalpy at this location, X plus dx. That's our Q advection in minus Q advection out. Does this term look similar? We have done for the X plus dx. We done this classic expansion when we derive the heat diffusion equation. What should we do next?
Just expand the second bracket, or we...
Yeah. Taylor expansion, we expand this term, the mean entropy at the location x plus dx. And we will just use the first term of its Taylor expansion. It can be expressed by this value at the location of x plus it's the gradient. Use D here, a gradient along the length of the tube times the dimension of our element. And we will neglect all the higher orders here. We will not consider higher orders. We just keep the original term and the first derivative. We have done this before. We enter the same place here. And now let's substitute this term into our Q advection in minus Q advection out. Then we can, you see the mean entropy here minus here. We can do cancellations, but must do Taylor expansion first. So we have our Q advection in minus Q advection out is by mass flow rate mean entropy at x minus mean. Now we will use its approximation mean entropy at x, then minus, but plus here minus. We have a term how the mean entropy vary with respect to x. How can we deal with this term? This still gives us nothing. Right? How can we relate it to temperature? Temperature is the value what we care about, not the entropy. We need to use the chain rule. Right? For let me finish this first. This would be minus dimx over dx times dx. Let's neglect phase change. Consider there is no phase change. No phase change gives us that the specific heat is constant, Cp. And in this way, we can translate, we can turn the entropy here into, because Cp is defined as how entropy change with respect to temperature, right? Because for internal flows, we all care about mean. So how the mean entropy change with the mean temperature. So with this constant, we can say that the mean entropy change gradient along the tube length is simply given by, do one more step, how it varies with temperature and how our mean temperature vary in the tube length. It's chain rule here. And this term is given by the specific heat, which is assumed constant because there is no phase change. So far, 4 assumptions. Because no phase change, then we can treat it as constant. With phase change, latent heat keeps going, but at the same temperature. Right? And in this way, with this term, we would have our Q advection in minus Q advection out. Here those mean entropy cancels. And this term we defined just as the specific heat times the mean temperature gradient, just by the minus mass flow rate times entropy, the specific heat times the mean temperature gradient over dx times the dimension of our element control volume. Let's keep it as it is. I know the dx is irritating. We deal with Q advection in minus Q advection out. The only term left now is convection. And since the second week, we know convection is the AS now is the surface area where convection happens times convective heat flux. And Monday, we note that in external flows, convection heat flux we define as our convection coefficient times, in this heating case, surface tube temperature, tube surface temperature minus that of our mean temperature of the internal flows. How about the AS? Inside this differential element, what's the area where convection happens? Like a cylinder, right? The side surface of the cylinder, not cross-sectional area, because convection happens between the surface and the internal flows. Cross-sectional area, that's for convection. For convection, always the surface area. So because we don't necessarily need make an assumption as a circular tube, let's use something new as the PdX. P is the perimeter of the tube. It can be any shape. We'll learn how to extend all these two non-circular tubes on Friday. P is the perimeter of our tube. And when it times the length of the differential control volume, it gives us the side surface of this control volume. That's where convection happens. And we have identified Q advection in minus Q advection out. We identified a convection term. Let's put all of them together. Q advection, then we would have our Q advection, this term plus this term, right? The minus. Then we end up with how the mean temperature varies along the length of the tube, not the radius. The length of the tube is given by the ratio of the diameter of the tube times the convective heat flux between tube surface and the internal flows over our mass flow rate and the specific heat of the flow. That's by defining control volume and energy rate balance, we end up with this. Nothing new, or everything is based on advection we learned in first class of second week. And as we kept here, but this just tells us half story, because I don't want to know its gradient. I want to know its exact value varies in the length of the tube. Then that depends on heat conditions on the surface, because as we have done at the beginning of the class, for different surface conditions, we have different curves.